Hello everyone, we will be discussing the research paper titled Bankrupting Sybil Despite Churn by Diksha Gupta, Jared Saia, and Maxwell Young. Sybil attack was first identified as a vulnerability in open systems by Dossier in early 2000s. In an open system, participants manifest in the form of virtual identities. This allows an adversary to claim multiple identities independent of the actual adversarial participants, thus resulting in a disproportionate influence over the system. This attack is prevalent even today, after 2 decades since it was first identified. One such large-scale attack was on the cryptocurrency systems in May 2019, amounting to 4.6 million US dollars. Existing defense techniques require continuous puzzle solving to limit the number of Sybil IDs in the system. Even in the absence of an attack, the most popular puzzling technique in cryptocurrencies is proof of work. A recent study claims that the carbon footprint of the Bitcoin network, which is based on proof of work, alone is comparable to that of Myanmar, with electrical consumption comparable to that of Algeria. This is a huge waste of resources. Thus, drawing motivation from this, we present an efficient Sybil defense scheme called Ergo. Our algorithm gives the following guarantees. Let T be the adversary spend rate and J be the join rate of good IDs over the system lifetime, both of which are unknown to our algorithm. Then Ergo maintains a minority of Sybil IDs in the system at an algorithmic spend rate of O of J in the absence of an attack, whereas in the presence of an attack, this cost is the geometric mean of J and T. Next, we discuss our model. The system consists of n IDs, which are either good or Sybil. Good IDs follow the protocol, whereas Sybil IDs can choose to deviate arbitrarily from the protocol and are under the control of a single adversary. This allows for collusion amongst the Sybil IDs. The adversary has at most a kappa fraction of resources in the system, which is a fixed constant less than 1 over 18. We allow for IDs to join and depart over the system lifetime, pertaining to which we make the following assumptions about the good ID churn. To define the notion of good ID churn, we look at durations of time over which the good ID membership changes by a constant fraction called an epoch. We define two a priori unknown parameters, alpha and beta. The first parameter defines how the good ID join rate changes from epoch to epoch. Formally, we assume that between any two successive epochs, the join rate of good IDs differs by at most an alpha factor. The second parameter defines the smoothness of good ID churn within an epoch. To this end, we assume that the number of good IDs that join or depart over a duration within an epoch differs from the expected by at most a beta factor. Note that this still allows for exponential churn of good IDs. Then, given this framework, we aim to propose a Sybil defense mechanism that always maintains 1/6 fraction of bad IDs in the system. For ease of presentation, we assume a server. In our paper, we have discussed the decentralization details using a committee. So next we present a Sybil defense protocol, Ergo, which stands for entire over rate of good. This name will become clear over the next few slides. To begin with, we initialize the system by issuing a one hard challenge to all the IDs in the network. This will reduce the fraction of bad IDs or Sybil IDs to kappa. Then we allow for IDs to join the system. To each new ID joining the system, we issue an entrance challenge of difficulty 1 plus the number of IDs that joined in the last 1 over JG seconds, where JG is the good join rate. Obtaining a close enough estimate of good join rate was a major challenge. Due to time restriction, we omit the details of our good join rate estimation algorithm, good jest. Once the system has seen sufficiently many joins and departures, we issue a one difficult challenge to all IDs in the system, which we call a purge. Any ID that does not provide a valid solution to this challenge is evicted from the system. This again reduces the fraction of Sybil IDs to kappa with which the iteration ends. With this protocol, we maintain a minority of Sybil IDs in the network at all times while maintaining the cost guarantees. The secret sauce of this algorithmic cost is a good join rate estimation protocol, good jest. A good join estimate algorithm operates under the assumption that the fraction of bad IDs is always less than 1 by 6, which is maintained by ergo. Then we have the following result. Fix an epoch. Suppose rho is the good join rate over this epoch. Then the good join estimate obtained using good jest at the end of this epoch is within a constant factor of the true good join rate. Please refer to the research paper for further details on this. Finally, we present our empirical studies which illustrate our theoretical results over 4 real-world networks: Bitcoin, Ethereum, Nutella, and BitTorrent. For ease of presentation, we just present our results for Bitcoin. We measured the algorithmic spend rate over a range of adversarial spend rates for ergo and compared them against 3 existing works: Sybil Control, which issues system-wide challenges every 5 seconds, REMP, which issues system-wide challenges over fixed intervals based on estimated maximum attack rate, CCOM, which is ergo with 1 difficulty entrance puzzle. This is the empirical result obtained by our algorithm. As can be seen in this plot, ergo outperforms all 3 existing works. Additionally, we propose an ML heuristic based on Sybil Fuse, a machine learning algorithm which was proposed by Gao et al. We call this heuristic ergo SF. This heuristic further outperformed existing techniques, as can be seen in this plot. Motivated by the success of the ML heuristic, we propose obtaining a generic lower bound for Sybil defense as a direction for future work. And with this, we conclude this presentation. Thank you.